Hi everyone. It's really nice to be here. It's a pleasure and an honor. So thanks so much for having me. I'll just tell a very short blurb about myself. You know, I'm Spanish originally from Spain, but I've been living in the U.S. for 10 years now. I am based in Boston, although I did spend 5 years out in the beautiful West, which I dearly miss. It's really glorious out there. Um, and yeah, and so I'm a geometer, and I would like to share some ideas and some observations that I think are really beautiful, and I'm excited to try and think together of how this might fit into a session for high school students or some game or some activity, so I have a little bit of experience, you know, working with high school and earlier K through 12 students. Um, I tutored at some math summer camps, and I've collaborated a little bit with primes, but still, you're definitely way more expert than I am. So I'm really looking forward to hearing any and all ideas. I will require participation. I would like to encourage you, if you can and if you feel comfortable with it, to leave your video on, because we will be doing some things together, and so it'll be useful for me to just see where people are at and whether the experiments are working for them. But you know, of course, if you don't feel comfortable, that's okay. But that would be my encouragement. Okay, so maybe we can talk about some math. So here's more or less the whole shtick. I just want us to understand a simple phenomenon, which is the following. So if you have a coffee cup around at home, it's nice if it's not transparent and as cylindrical as possible, but any coffee mug will do. If you have a coffee mug, then please go grab it real quick. And this will be the first part of our activity, because I think it's important to realize that, yeah, this is not some kind of fancy math thing. This is just an everyday phenomenon that we can all experience. And once you have your cup, just take your phone or any other source of light and just turn on the flashlight. Okay, on your phone. Could be a flashlight. The more concentrated the light source, the better. Okay, and now that you have that, shine the phone, so shine the light inside the cup, and see if you can observe. Let's see if I can get it on camera. If you can observe a heart shape. So it should be there's a little bit too much light here for the camera to catch it. Let's see if I can get a better angle. Yeah, there you can see it. Does everyone see that little yeah, you can just about see it there. Yeah. So if you have a mug on you, I encourage you to do the experiment. Okay, so this is just a thing. This is just a thing that we shine the light and we see. Okay, so you have your mug. You shine a light, or whatever it is, on the mug, and we observe that at the bottom of the mug, we see this kind of shape. Okay, so the activity that I want to propose is an activity to understand why we see that shape. And it's something that I think is very hands-on, and kids of any age can do it. But before, maybe let me just give some conceptual background of like how I think about it, because I think, or at least why it's plausible that one might see this shape, and then I'll propose the activity. And by the way, please, anyone, stop me at any moment. If you want to ask a question, just unmute yourself and talk. I might miss the chat, so please, don't put your hand up or whatever. Just go ahead right in, and like the more interactive, the better. So yeah, please feel free to interrupt.
Monitoring the chat. If somebody has voice trouble but puts it in the chat, I will relay it.
Great, thanks so much. Okay. So I want to think of what's going on in the following way. So we have a light bulb or a light source, whatever it is, and then we turn it on. Okay, and as we turn it on, there is a sphere of light that starts advancing away from the light source in all directions at the speed of light. Okay. So, one nanosecond after I turn it on, or whatever, that sphere is very close, and then as time goes by, it advances. Okay, and so I get these concentric spheres, all centered at the same point, which was the light source, and these spheres are expanding, and if nothing were to happen to them, if there was no reflection or no refraction, then they would, all of the rays would just keep going their own ways, nothing would happen. But in this case, what's happening is that some of these rays, let me draw this a little bit bigger. What's happening is that some of these rays are going straight down to the mud, but some other ones are actually reflecting off the side of the cup. Okay, and what happens is that then this sphere of light gets folded on itself, and in fact it gets folded in such a way that when that front of light actually lands on the bottom of the cup, it lands with a pleat. Okay, and what I mean by a pleat is just the wrinkles that we all have in our clothes, right? So this is a pleat. You can only see half of it because my clothes aren't transparent. Wouldn't be very appropriate if it were. But there's kind of another fold behind here, right? There's one fold in the top, one fold in the bottom, and the two folds kind of die against each other at that pleat point right here. And so it's exactly the same, but with light. That wavefront of light has folded on itself, and then it's landing on the bottom of the cup with that fold. And so you see, if I have a point over here, it only gets one layer of light. But if I have a point inside this region, there are actually 3 layers of light that get there. So in this region, you have 3x as much light. As outside the pleat. And so of course it's brighter because it has 3 times as much light. And so that's why we see that cusp in a nutshell. Or at least that is a plausible explanation for why we might see that cusp. And what I want to then the exercise to propose it is to actually convince ourselves that indeed this is what is going on. But this is just the general overview of the situation. Okay, so any questions or comments at this point? that anyone might have.
So I have a question. This is, I guess, in a perfect situation where the cup or the cylinder is directly facing the source of light, or like when it moves, is that when there's more refraction or bending of the light?
Okay, so that's an interesting question. So if you were to place the source of light
Directly
above,
Yeah.
then you wouldn't see anything, because it's somehow too symmetrical and too degenerate. You would just see a mess. And you can do the experiment with the good thing about this is you can just confirm. You can put the light source immediately above the center, and I encourage you to do it. And then you will see that the cusp disappears. But then if you put it a little bit off center, then the cusp appears. So you will always see the cusp as long as the source of light is slightly off center. In this particular in this particular example.
Daniel, I have a question. This is Annie.
Yeah, hi.
Good morning. Would it matter if the cup is like shallow cylinder, and then if the bottom is concave, or if it's just flat, would it make a difference?
So I believe that you should see the same shape, even if the cup is shallow. You just might have to adjust the height at which you are putting your phone. If the bottom is curved, it might be a little bit more tricky. I think it would depend a little bit on the cup. I think, you do the experiment and you try out, but it's definitely true that if cups have like slightly more interesting shapes, then you might not see the effect as clearly. In my experience, at least, it works best with just a perfectly cylindrical cup. But I mean, like on this one, which is not quite cylindrical, it works just fine. Like, I think as long as it's not too wonky, it's gonna work.
Okay.
Yeah.
Thank you.
Will it work with other objects? Do they have to be cups? And that might be a segue.
Yeah. So of course it doesn't have to be cups like these. So this is an example of a caustic. Okay, this is what we call them in my trade, and these are objects that we see all the time in all kinds of situations. Whenever light reflects or refracts through whatever medium, for example, water, and I will discuss a little bit more about that later, but absolutely doesn't have to be a cup. It's just, I like the cup example because like everyone has a cup around somewhere, and everyone can like shine a light these days on their phone or whatever. So it's just like an experiment that I feel can be universally done, which is nice. But you can definitely, search around the house for weird objects and then shine lights and see what kind of shapes you get. It is a theorem that you will always see a curve with some cusps. So the shape of the curve might be different, but you will always get, some curve with some cusps, it turns out. But of course, the particular configuration will depend entirely on the shape that you use. Okay. Any other questions or comments?
Oh, for like students that might ask about the applications, could this be like applied to fiber optics or?
Yeah, I mean, this can be applied to all sorts of things. I mean, it can definitely, all of these ideas have a lot of applications to optics. I mean, the way that we design lenses is all about how light refracts to be able to concentrate it on a focal point. When people design like a sound system, you want to think of how the sound wave will maybe concentrate at certain points and cancel out at others, and that kind of interference is very relevant for acoustic design. Yeah, like these ideas definitely come up all over in all kinds of situations. I don't know about fiber optics in particular, but I imagine you have to think about it a little bit but yeah, I'm not so familiar with fiber optic in particular, so I can't comment on that example. But yeah, there's definitely all sorts of places in real life where these things come on.
I did an experiment, or this is Joyce Adiazi from Cancer Middle School.
Hi.
Hi, I did an experiment with solar ovens, and we did where we had different openings of solar ovens, like how wide of an opening of solar ovens, just so that we can get the correct angle of the sun, not blocking, but reflecting into the solar oven and into directly into the middle of the oven, so that we can get it into the to where the students were baking their whatever item they brought. So we brought, or the students, they brought in, or they came up with a whole bunch of different ideas, and some of them were like 3 feet tall, some of them were 2 feet tall, and it's just trying to get the correct angle and pointing it towards the sun, and just so that they could the rays to get so it could bounce off the walls of the the sides of the boards that had foil to go into the solar ovens.
Right, and there, yeah, you have to calculate these angles, whether you do it by trial and error or whether you do it by formula. But yeah, it's the same kind of geometry going on, of course. Yeah, that's really cool, because that's a very real application of, then you can eat the baked goods that mathematics allowed you to concoct, right? So you have a very
they made s'mores. Somebody even brought lasagna, hot dogs, cookies. It smelled good outside that day.
Super cool.
Me, Daniel Hunter Ben pointed out to me when we were walking around the border of Canyon de Chelly that thousands of years ago they were using deer skin and the pockets in the canyon as solar ovens to cook things. So this has been solar ovens are part of the culture, I understand, for many, many years.
And then I see also a comment that on the chat that says that someone noticed when you move the light, you actually get a 3-dimensional shape. So indeed, if you move the light, then this curve will move, and then you can get movies of 2-dimensional shapes which assemble to 3-dimensional shapes, and that's something that I will also try to touch on a little bit later on in the session. So yeah, so that's indeed a very, very pertinent comment. Okay, so the next thing I want to do is for us to do an activity together to try and convince ourselves that is indeed what's going on. Any final comments or questions before we move on to that? Okay, so fine. So I told you a story, and you maybe believed me or not, I don't know, but while this is maybe a reasonable story, for a mathematician at least, this is not a proof. We need a proof, and so the exercise will give a proof that indeed that is what's going on. So there are several versions of this exercise, and so far the ones I have conceived are very, very basic and very low tech, but maybe some of you who are more savvy with tech, or maybe who are more savvy with crafts, can help us think through what might be improvements. But at the minimum, okay, so what do you need? So in the more basic version, you just need a piece of paper, maybe 2 or 3 colored pencils, and a ruler. That's it. Okay, more basic version, and hopefully some of you have these materials here with you, and if you do, then please have them available. And then a little more fancy, if you want to do something with your kids or whatever, you can use tracing paper. And even use a protractor. So let's try and concentrate on doing the more basic version now, but I will comment on how to do the slightly fancier version as we go. People can read the board, yeah? It's legible?
No, someone's launch meeting is on. Can't see your board.
That is being shared.
It's Patricia Begay's screen that is on. Therefore, we can't see your screen.
Okay.
Look over, now it should be back.
Okay. So can people see the board okay?
Yes.
Okay,
Yes.
great. So paper, 2 or 3 color pencils and ruler. So okay. So let's take a piece of paper and let's draw a circle. Okay, you can draw a circle, as I'm sure you're well aware, either just by hand or by using a piece of string and a pin, and just putting the pin in the center and using the string to make sure that you're doing a correct circle. Or you can use a protractor and just flip it over and do a circle, but just freehand is fine. I mean, for the, at least for now, and for the accuracy that we're going to be dealing with just in the session, it's not very important. But then if you want to do this as maybe a more involved project with your students, then maybe you can make sure your circle is very pretty. So something like this. See if I can turn. Okay, so I have a circle, and then what I would like you to do is mark the center of the circle. Okay, so mark the center of the circle with a point, just like that. Okay, and then we're going to mark another point, which is a little bit off center. So this is actually related to the question about does it matter if the cup is very shallow? We're going to do an experiment where the cup is really shallow, and in fact it's almost flat. So we're just going to pretend like everything is happening just on a 2-dimensional plane. Okay. And so the next thing I would like you to do is to join every point on draw a bunch of points on the outside of the circle, like so, and then join them by straight lines to that off-center point that you have marked. Okay, doesn't have to be many points. I think if you do something like I did here, it's going to be fine. If you do less points, it's also going to be fine. But the more points that you mark on, the better chances you're going to get of ending up with a picture that accurately reflects the geometry of the situation. Okay, so yeah. So while you do that, let me just draw some things. Okay, so while yeah, so we're joining our point with lines. It does take a minute, but while you do it, let me just remind you of how reflection works. Okay, so the way reflection works is that light comes towards the surface, and it is going to bounce out with the same angle to the normal, okay, which is the perpendicular line to the surface at that point. It's going to bounce out with the same angle to the normal as the angle that it came in. That's how it works. It's just an experimental fact of life that's how it works. So this is the law of reflection, and so now we're going to use the law of reflection in our next stage. So how are people doing? Are we getting some? Are we getting some lines? Yeah, I'm seeing some good ones. Yeah.
Once I made the lines, it didn't look so centered.
Yeah, it shouldn't be centered, yeah? It should be off center.
Yeah.
Yeah. Let's see if I can see it. Oh, somehow yours is a little blurry because of, let's see if I can make yours bigger.
Is it?
Can you show me again, Barsky?
Is it?
A little further away. Try to put it a little further away.
Is it blurry? Here, let me turn off my blur.
Yeah, I think somehow, you know, Zoom is very smart and it wants to blur everything that's not a human. So yeah, great. Okay, cool. So now we're going to do the same thing. Okay, we're going to do the same thing, but with the other point, the actual central point. So if you see my image, now I've taken, so in red you have the lines from the point that is off center, and in yellow you have the lines from the point that is at the center. And so every point on the circle, we're going to connect to both the center of the circle and the point that is off center. like so. Okay, so I'll just wait for a little bit while we work on that.
Dito sa area? Sa itong Phil Thomas siguro, ang stage siguro. So dito sila nag-practice ka eh? Oo.
If anyone has any questions or is facing any issues, then please please let me know, obviously. Okay, so I also drew a cartoon there on the board, just so that I only drew a few of the rays, but we can get an idea of what it should look like.
Okay, I got it.
All right, let's see. Let me pin you. Yeah, you got it. Beautiful, beautiful. Yeah. How are others doing? Oh, let's see, Senan. Let me try and pin you. Oh yeah, beautiful, beautiful. Yeah. Okay, just gonna. Oh yeah, Ty. That's cool. Yep. Beautiful.
Daniel, this is Virgilin. I got mine, but when I hold it up because of my background, it doesn't show it very well.
Yeah. Oh yeah, I can kind of, yeah, it's yeah. I mean, it kind of appears and disappears, and you also disappear.
Yeah.
But yeah, I think that's fine.
All right. Thank
Okay.
you.
Yep. Okay.
I tried to show it on my camera, but because of my background, see, it didn't work.
Yeah, let's see. It's kind of funny because, like, you know, you put your paper and you disappear.
Okay, there you go.
Yeah. Okay. Yeah. It seems like everyone is getting there. Is everyone having any problems? Everyone happy? Okay. So now we're going to use the law of reflection to draw a third set of rays. Okay. And how are we going to do this? Well, so what's going on, right? Like this off-center point, this is my light source. In real life, this was kind of elevated above the cup, but whatever. We are two-dimensional beings. We're just simplifying the experiment, thinking that everything is just happening in the bottom of the cup. And so I'm turning this light on, and then what I need to understand is how it's going to reflect off of the side of the cup. And so for each ray, okay, what I need to do is apply the law of reflection. I need to look at this angle, and then either eyeballing, let's just eyeball it now. But if you want to be, you know, if you want to make an art project out of this, you can use a protractor and be very precise, or later we can think of what could be other mechanical ways of doing it. But today, just eyeballing it, draw a ray, okay, in another color, in a third color if possible, because it's going to get messy. Or if you have tracing paper, now is the time to get tracing paper and do this third layer on a separate piece of paper. But if not, just try and use another color if you can. And for each of your points on the outside of the circle, draw this third ray by making sure that you obey the laws of reflection.
So I have a question. Will this make it into a chord or a line that?
So is the question how long to make the ray?
Yeah, will it be a chord?
Yeah. So that is a great question, actually, and this is the kind of thing where a posteriori, like after we do the activity, you might realize that maybe it would have looked cooler if you had made your rays maybe shorter or maybe longer. For now, let's just make them about the same length as the radii that we've drawn. So that they don't need to go to the other side of the circle. They don't need to be a full chord. They definitely don't need to go beyond the circle. Just even a little bit like this will be fine. But at this point, you know, this is both a science and an art. So like I said, you know, you might find later that there's some lessons learned. But yeah, the size of the rays will play a role in how pretty your final picture is.
So you start connecting or making your segment from the intersection of the line with the epicenter and the outside center.
Right. So at every point on the circle, right? So you have these two rays, one going from the center and one going from the off center, and then they intersect at that point on the circle, indeed. And so now you're going to draw a third ray from that intersection point. And the rule is that the angle that the first ray was making with the radius, it needs to be the same that the angle that your new ray is making with the radius. Those are the rules of the game.
Makes sense.
Okay. Is it clear to everyone? Does anyone have questions about what the rules of the game are?
Daniel, on your paper, can you show us kind of what it looks on your paper?
Yeah.
If you were to do that.
Yeah,
Thank
yeah,
you.
yeah. Well, yeah. I mean, so I kind of want to wait to show you the full thing to see if someone gets it. But I will start drawing the first ones and show you. I actually have to do it. So let me myself. Okay, so this is what the first few rays would look like. And again, you know, this is very approximate. Like we're just eyeballing it. Of course, you can be very precise and actually use a protractor, but I'm just eyeballing it. The thing to notice, right, is that these rays further outside here have a larger angle with the normal than the rays over here. And in fact, if you look at the horizontal one, that one is perpendicular to the circle. So there the angle is 0. So that ray is going to bounce right back. And as you get further away from that point, that angle increases. And so that will mean that the way that the rays are bouncing changes as you move around the circle. Does that make sense to everyone? Or are there any other questions or? See,
Daniel, it does make sense, but my rays are a little shorter, but they look more shorter than yours.
Yeah, Ty, I see yours. Yours looks beautiful. Yeah. Let's see what else.
I don't know if you can see mine's.
Let me see. I'm trying to find you on the.
It's Veed and SP.
Yeah. Okay. Yeah, I got you. So try to show me. Let's see if I can see it. Yeah, it's just you kind of disappear.
Yeah, it just kind of disappears.
Yeah.
No, can't see it.
No, I just see your background, unfortunately.
Sorry.
No, that's fine. Maybe if you put your hand in front of it. Oh, there I saw it for a second. If you put your hand in front of it, it might try to identify it as a human. Yeah, kind of. Yeah, don't really see it that well.
I guess background's not helpful right now.
Okay, yeah, I'm seeing some beautiful ones. Yeah, Dwayne, Aaron, yeah. Okay, and if you've already finished, then I encourage you to do the following. Okay, so if you again look at my my video, so what you can start doing if you've already done it is then you can start drawing some rays in between. So for example, in between these two first rays, I don't really need to draw like another point. I can just kind of eyeball that in between those two, there's going to be one that kind of goes in between. So let me show you what I mean. Let's see. Yeah, so you see now here in blue, I'm kind of adding some extra rays, just kind of interpolating between the ones that I already had, right? Like I already have like a guide at a certain bunch of points in the circle for how these rays are going to bounce off. And so now I'm just going to add a few more just so that the picture gets a little bit clearer. Because, you know, as I'm sure all of your pictures are getting really messy because, you know, this is a messy business, but depending on how you do it, sometimes less is more, but sometimes actually having more rays does bring the geometry out more clearly. So yeah, just try and fill it in, and then see if you notice anything in your picture as you start filling it in with those in between rays. If you're really lucky, a cusp will start appearing. And if it doesn't, then worry not. I'm sure we can learn some lessons so that we learn how to be able to produce it more consistently. And again, if anyone has any questions, just ask. I'll keep having this one here as a guide.
This one, we just make a line anywhere, did you say?
Just like in between the reflected rays that you've already drawn, you can add a few more going in between. So you know that the lines between the reflected rays between any two of the ones you've already drawn are going to have slopes in between the slopes of the rays you've already drawn. So again, this is like a little sketchy, but you can just kind of eyeball what those rays in between are going to have to do, because this is all going to have to move continuously. The slope of these rays is going to be changing. Yeah. I hope I'm not muted.
You were not muted.
Yeah.
It's working well.
Yeah, just saw that chat. Okay, so is anyone getting any kind of recognizable shape? Yeah, I see some nodding by Ty.
Interesting comment.
What's a spirograph?
Yeah, spirograph is like an old school 60s, early 70s kind of toy that has like plastic gears and holes where you stick pencils in, and you can turn and move things around and make diagrams. Very much.
Rev, I can't see it because it's blurry. I don't know if there's a way to unblur it. Sorry, Dave, I cut you. Oh yeah, yeah. Uh-huh. Yeah. Okay. Any others?
Also, somebody labeled iPhone as saying Dr. Fowler did something similar. So when Henry talks about the geometry of Hogan, when he goes in further, an important element to it is the way the sun enters the chimney hole, and when it sweeps out, I think it's called the anom. It gives, over the course of a year, sort of figure-8 light and caustic that is used when they look to decide when to plant and harvest crops historically. Ella is pointing out like a clock through a chimney, and so this is something that is been done and used in the culture in different points. It's really cool for people who know.
So David, I wonder if you could pin Ty for a second. Ty, would you mind showing yours again? I think yours is very clear. You can really see it.
Let me see if I can figure out how to pick.
Or how to, or if people just want to look, like so in Ty's, like you can really see the cusp appearing there. Okay, so you can see it in green, and if you draw more lines, then that shape will appear more clearly.
It looks like the right side's a little sloppy, but I don't know. That's freehand.
Yeah, no, that's really beautiful. Let me show you the one I made with tracing paper. So if I used a tracing paper so that you didn't have the other lines kind of on top, because it gets messy, and you really see that cusp appearing. So I mean, it just is what it is. Like that's the proof, QED, end of the proof. Like that's and the cusp. So that cuspidal curve. Notice that the property that it has is that it is tangent to every single line. Maybe you can pin me again now, David. I don't know if
yeah, I did.
Okay. Yeah, you might have to try again. So it took me actually a few tries myself. I'm not going to lie, until I could get something that looked half decent. But it's the kind of thing that you get better as you do it more often. For example, this is related to this comment about how long to do the raise. You can notice in my picture that because I drew my raise not that long, it's less messy, because I kind of only drew the length of the ray that I needed for that cusp shape to come out. So there's a little bit of trial and error, knowing how many points to do it at, practicing your freehand. You can also cheat a little bit, like if you know what shape you're trying to get out, you might just fudge your freehand a little bit to kind of force it. So you can definitely cheat a little bit, but it is something that I think, you know, everyone can sit and do, and it would make yeah, it would make like a pretty collection of pictures that you can hang up or take home or whatever. Okay, so that yeah.
I have a question.
Yeah.
This is Joyce Setayazi from Canton Middle School.
Hi.
Since this is a circle and you can place the dots at any part of the circle, it can be infinite, right?
You mean you can put infinitely many points on the circle?
Yeah.
Sure. Right. So I mean, yeah, there are infinitely many points in the circle. We're just trying to draw a few rays so that we see the shape emerge. Of course, this is only some approximation with finitely many rays, but already just by drawing, you know, a small number of them, we can see that cusp shape appearing. Of course, and yeah, and this is kind of an interesting segue to some questions I had for you. So yeah, I like to draw. I wanted to be a comic artist before I decided to be a mathematician, but then I realized that, you know, geometry has better pictures. But anyway, I just really like to draw by hand. I like Blackboard. I like this kind of activity, but I think it's quite possible that there are other different ways of doing this kind of activity. Maybe using some software that some of you might know or might be comfortable with, or maybe in some craft way, like you know, David and I were trying to brainstorm. Maybe if you had a cardboard circle and you put a pin in the center and you try to do this with string, but then it wasn't really clear to us how to mechanically make this law of reflection work just in a crafty kind of way without using a protractor. So like, if anyone has any ideas of other, you know, twists that one could put on this activity, then I'd be really interested to hear your thoughts.
This is Mr. Mendoza from Tinian. I just would like to know if those lines that you actually made are actually meeting at one point of tangency.
These reflected lines? I don't think they're meeting at a single point. So the cusp is this red line has the property that it is a curve that is tangent to every single ray, but the tangencies occur at different points along that red cusp.
Okay.
So yeah, I don't think there is a single point like that. No.
Thank you.
Mm-hmm. Yeah, so Brian says that we can use yarn. So I agree we can use yarn, and you can use yarn to draw those radii and to draw or to build with yarn. But then how do you, do you mean just build a model like as an art piece, like just do this whole thing even with a protractor or eyeballing it, but just actually have the yarn? I see. Yeah. I like it. Yeah, that would look really beautiful. You could hang it on the wall. Yeah, I totally agree. Any other thoughts or comments or suggestions or?
It'd be fun. It almost seems like it could go into textiles with weaving, but I'm not sure what loom you would have to build to make that structure fit.
Mm-hmm. Mm-hmm. Anyone else?
I think I misfollowed a direction somewhere because mine didn't come out anywhere near that.
Let's see. Can we have a look?
It just comes out like this.
Okay, let me just try to.
And I'm wondering how.
Yeah, so I think so take the point let me see if I can understand what you're drawing. So take, for example, the point that is at the very bottom, right? So the point that is on the ray between the two, or the two central points, the red one and the blue one. Like there, your ray should bounce straight up, because here, for example, at this is like the point that I'm talking about. Here, this ray should just bounce straight back because it's perpendicular. So I think yeah, you didn't quite obey the law of reflection. So again, let me repeat the rules of the game. So if you want to draw, say, the ray at this point, you need to look at the angle between the radius and the incoming ray, and then the reflected ray should have the exact same angle.
Oh, okay. Okay, that's where I got it wrong.
Okay, and so as you go closer to here, this angle is going to get smaller. And so if you do it right, at the end of the day, what you'll get is something like this. It kind of highlights this kind of shape. Okay, so we have a few minutes left, and I just wanted to give maybe some ideas of related activities that that we could do in this spirit. But I'll ask again, just if anyone has any other, questions or comments or suggestions for other spins that we could take on this. Okay.
Maybe software to use could be like GeoGebra or GMX. GMX, you can make all the shapes. It might be a learning curve. I still have to play around with it too, but those could be like software. And then, I don't know, Math Circles had logo at one point, I think. But yeah, those are some suggestions. I can put them in the chat.
But the thing is, like what would you do? Just select like finitely many rays, and because like if you put all of them, it would just be a mess, right? So I guess you'd have to do something similar like this, like just selecting finitely many points. And
one thing you could do that's really quick is you put your one off center point, your radius, then you do the reflect in the line through the radius, and the one point that's on the circle, you can put that as a variable, and you can either animate and just slide it around, or you can move it and make just copies of it and copy the whole thing that, everything that's constructed using the points. The software is pretty powerful. And so somebody that's using GeoGebra or Desmos or something similar with the geometry class, the students would already be doing stuff like this, could learn it pretty quickly.
okay, so I want to just mention two more pictures that I think one can try to draw that are cute. So So like I was mentioning, another way that you could get this kind of caustic pattern is not through reflection, but through refraction. And so if you've ever looked at a swimming pool and you notice these patterns dancing around on the bottom of the swimming pool, then this is another example of this kind of geometry coming into play. And what's going on is the following thing. So here we have the surface of the water, okay? And the light is coming straight from the sun, so vertically straight down. And you can try to draw this with me if you want to, as I go. Okay, so that's the light from the sun coming. Okay, and so now what we need to understand is how are these rays going to refract through the water. Okay, so refraction is a phenomenon that makes the direction of a ray of light change as it goes from one medium to another, in this case from air to water. And so the law of refraction is a little bit harder to state precisely. There's some signs and it's called Snell's law. Like you can try to do it precisely if you want to, but again, I'm just going to be very just eyeball what's going to happen. And the only thing I need to know is the following thing. So here's air, here's water. The only thing I need to know is that the angle that I'm coming in with is going to be larger than the angle I'm going to come out with respect to the normal. Okay. So again, if I'm coming really perpendicularly, then those rays are not going to change. So the rays in this picture that are hitting the wave of the swimming pool at the very top and at the very bottom of the waves, those rays aren't going to change at all. Those rays are going to remain just like they are. But these rays are going to change, and the more the normal is inclined, the more twisted they will change. Okay, so it's something like this. And if again you do the exercise of drawing a lot of them, then what you'll see is the same type of cusp emerging as the curve that is tangent to all the rays. And in this case, what is happening is that if you think of the light front, like a single wave of light coming from the sun, like all of the light that the sun put out at a particular moment, as it undergoes this reflection, it will end up being folded on itself, like so. And so when it lands on the bottom of the swimming pool, you will get some areas that are brighter because they have 3 times as much light as the other areas. And so that's why you see those patterns in the swimming pool. Of course, the picture is more complicated. There's waves in multiple directions. It's kind of crazy out there. But this is, again, the same basic phenomenon that is going on. And this is, again, a picture that you can try to draw with kids if you give them some rules. And you will, again, get the same cusp as we saw before emerging. And well, okay, like this is again some like the light in the teacup. This is something that we're used to seeing all the time when we look at water and the shape that light makes on the bottom of the body of water, at least if it's not very muddy.
Just a quick, right, swimming pool pictures.
Yeah, that's a good. Yeah, so those So if you imagine, that a swimming pool just had waves in this direction and then waves in the perpendicular direction, then you would just get a grid as the pattern. But of course, the actual waves are much, much more complicated. So instead of getting a grid, you get all of these pretty pictures that that David was just sharing. Okay, any questions about that or any comments?
I guess, like, I have a question. So when light reflects through like lens or I guess these like surfaces where there's like two planes, does that make it so that you have to keep reflecting and reflecting as you go through, as light goes through these layers? And then you follow
Say it
the
again, sorry, when you have a lens that has what?
like a lens has two planes, right? So like if light goes through it, will it refract twice?
Yeah, it will definitely refract every time it changes medium.
In fact, some cool applications of this is you can draw like a teardrop shape, and you can get pictures of this online. Maybe I'll look. And when you reflect through a couple things, that's when the sunlight goes through a raindrop and gives you a rainbow. And then if you're on a really bright day or above or high in different views, it continues doing multiple, does infinitely many different reflections and refractions. Sort of the next order when it cycles around will give you second branches. So if you've ever seen a double rainbow, and there can even be multiple rainbows. You can see, you may have seen that, actually in the Navajo reservation, there are great thunderstorms and rainbows that I've seen when I've visited out there. So
okay, so that's another example of where you get caustics with refraction. So we've seen one with reflection, we've seen one with refraction, and then with the time that we have remaining, I want to discuss one last way in which we can get pretty pictures formed by light interference. And so let me draw again. So I want us to do the following thought experiment. Suppose that I have a circle, maybe it's a ring of metal, and I put light bulbs facing in. Okay, all around the outside. Okay, all around the inside. I have light bulbs all around the inside of this metal ring facing towards the center. And then I turn them on all at the same time. Okay, so then what's going to happen? Well, after I turn them on, there's going to be this front of light that is going to be advancing at the speed of light towards the center. So if I draw the movie, it will start as a circle like this, and then it will get smaller. It will get smaller. It gets really small. At some moment, it's going to actually all degenerate to a single point, because all of those rays of light got to the center of the circle at the same time. And then it's going to come back out. And get bigger. Okay, so for example, if I follow this guy, right, so it's coming like this, like this, like this, like this, now it's here, and then it keeps coming this way. Okay, so so if I draw the whole movie, I get like a cone. And this is related to so here now I'm trying to understand, what is this movie that I get if I put everything together. So with time. So this isn't very interesting yet, because a little bit like we were discussing before, if we get the cup and I just put the light immediately above the cup, it's just too symmetric. Like you don't really see the geometry of what's going on because it is too symmetric. And so in this experiment in which you turn on these lights, we don't really see the geometry. It's all concentrated at that point because the circle is too symmetric of a shape. And so the activity that I want to propose is to try to think of what happens if instead of a circle, I start with a slightly less symmetric shape, for example, an ellipse. But you can go to the races and consider absolutely any shape and do the experiment, and you're going to get all sorts of interesting patterns. So that's the activity that I want to do next. But any questions so far? Is that more or less clear? What I'm like the situation that we have?
I have not a question, but a comment. I also teach physics in my classroom. This is Joyce Yazi, Kienta Middle School. I teach 6th grade. So I've done a project to where I start from my doorway, and we bring in a spotlight. And what we do is I position students, well, I don't tell the students what to do, but I tell the students to position themselves in different parts of the classroom and have the line or have the light reflect off of the mirror and go to reflect off the mirror and go to the next mirror in different parts of the mirror or different parts of the classroom, and try to at least 7 to 8 reflections off of the mirror. And we start at the doorway and they have to end at the doorway and see if they can get the rays all the way back to the doorway. So each year when I do this, we've been successful 3 times out of 7. And they see that when we start with a big spotlight, they see that at the end, the spotlight becomes smaller. So it's really tiny. So what you had just explained there on the board behind you, that's what happens.
So
yeah.
that's why it fails when it fails?
Yeah.
Yeah, I mean, a lot of these experiments I feel are kind of stable if you get the initial conditions right, but somehow there are some bad configurations in which just, like either it's too symmetric or there's some cancellation, and then like the whole thing doesn't work. So yeah, it can be a bit tricky to do experiments, but then when they do work out, it's very pretty.
Yeah, but they like it. I mean, they're out of the seats, the classroom's dark, and they're trying to position the mirror at an angle in different ways to get the light beam back to the doorway.
Cool. So I think I'm about out of time, and I want to respect our schedule. So let me just very quickly finish just by proposing the activity, and then I'll let you folks maybe try and do it and see what happens, and then I'll follow up with you all after our session, maybe with some pictures of some handouts that show you what the activity should look like if it's done properly, and maybe even some additional pictures to explain. But let me just explain what the activity would be. So what the activity would be is you draw an ellipse. Okay, and now this, in some sense, this is much simpler than the other one. The only thing that you need to do now is draw the normals. That's it. Just draw the normals to this ellipse. But again, there's a little bit of an art in not making it too cluttered and not making it too messy. I suggest maybe start by only drawing the normals to the lower half of the ellipse. And I will just do a few to show you, right? So here's a normal, 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 okay? And so in the activity, try to understand what shape is going to emerge. Okay, so before we had a cusp, here it's going to be a line that is tangent to all your normals. And if you do it, if you do it right, then you will see a shape appearing. And again, it's a caustic that in this case is caused by the fact that your source of light was not a single point. It was light bulbs on a curve. And so I invite you to do this activity for the ellipse. And then if you find that it's fun, you can do the activity for any other shape that you start with. And you'll start drawing normals. And then if you see what shape emerges, you'll find some curve with cusps, and it'll be a different curve depending on what shape you start with. And anyway, there's a whole circle of ideas and activities that you can lead in this direction depending on what shapes you start with. But yeah, I think I will stop here because I'm out of time. But thank you so much for your attention, and yeah, and I will follow up with some handout trying to summarize these activities in case that's useful.